on, here we go. All right, so if you remember from your pre-cal algebra days, you typically study logs on the heels of studying exponentials, and there's a good reason for that, right? How do you unexponentiate something? You log it. How do you unlog something? Exponentiate, right? And therefore, they're what's of each other? Inverses. Inverses. Yeah. We know what the graph of a log function looks like, right? You take the graph of an exponential function, reflect it across the line y equals x, and you get something that resembles this brown graph right here, yeah? If you take exponential growth. This is logarithmic growth. So instead of having a horizontal asymptote on the x-axis, log functions have a vertical asymptote on the y-axis. And for the growth functions, they come from negative infinity and they intersect the x-axis at what point? You remember? It's the old y-intercept of exponentials. 1, 0. Yeah, exponentials go through 0, 1. Therefore, logs go through 1, 0. And they increase at a very slow rate. Yeah, these things go up, up, up forever. So the limit as x goes to infinity of this function, we'll just call this log of x, it does go to infinity, just very, very, very slowly. So if you were to graph one on a calculator, you might think that there's a horizontal asymptote up above, but there's not. So logs are actually designed, by design, they're there to slow things down. Exponentials grow very, very rapidly. Logs counter that. They slow things down, okay? So there you go. If I just write log of x, let's talk about it. The log does have a base, just like exponential do. What would be the implied base right there if I don't write the base? 10, right? I'll just write that like this. This is implied base 10. Okay, which is known as the common base or the scientific base. So we can say right here, log of x is equal to log base 10 of x. And it's okay to write the 10 if you need to. Like sometimes if we're doing calculations, we want to see the base, right? So there's nothing wrong with writing it, but typically we don't write it. So that's one of the two that's okay not to have a specified base. That's the one that the scientists use, right? Your calculator even uses base 10 when it gets overflow, like it'll put e to the something. That means times 10 to the something. So scientific notation is also base 10, but a lot of things are base 10. pH levels, light intensity, sound is measured in decibels, which is a log scale. So lots of things with base 10. The other one that we're going to be using is, oops, too many squirrelies. There we go. ln of x, right? Or you can write it like this if you don't write cursive. Just I write the cursive because the L looks like a 1, right? It looks like my number 1. So I write in cursive. But it's the logarithmic naturalis, which is the natural log, right? And that's log base e. So those are the two that your calculator can handle as well. Your calculator is pre-programmed with both of those bases, base e versus base 10. So that's your natural log. Natural log base e. Everything else requires a subscript after the log to specify the base. Hey, speaking of natural log, here's a picture, a depiction of a natural log, one that occurs in nature. Yeah. And it took me quite a while on Google Images to find a log that actually had a little piece of its branch that actually curved in the right direction, like a natural log function. I mean, I must have spent probably 30 seconds to a minute, you know. Clash of Clans do as well? They do. Oh, nice, nice. Clash of Clans log. Nice. Okay, maybe during lunch. Yeah, that's good. I didn't know that. Maybe this is a Clash of Clans log. I don't know. It might be. Yeah. Okay. All right. So let's go ahead and define a log function. All right. Let's go ahead and define a log function. If the base is greater than 0, but not 1, and b to the x then is a 1-to-1 function, we know that. What does 1-to-1 mean again? Yeah, and only 1x for 1y and also only 1y for 1x, right? So that means it passes both the vertical and the horizontal line test. Okay, that means when you reflect it across the line y equals x, you're going to get a function because that's what a horizontal line does. It reflects across that line to a vertical line test. So doing a vertical line test on the output is the same as doing a horizontal line test on the input. All right. We call those functions invertible, remember. So here we go. This is the what we call, for lack of a better term, this is what I call the conversion formula. And this is maybe what you remember from pre-cal or algebra 2 even. It's an if and only if statement, so it's really a definition. B to the x equals y if and only if log base b of y equals x. Okay, so you can start with either one. If the top is true, then the bottom is true. Or if the bottom is true, then the top is true. All right, so most people learn to go from logs to exponentials, right? And this is kind of how a lot of people do it. They do what I guess sometimes it's called the around the world. You all remember that? Around the world. It just kind of takes you on a circular path. So b to the x equals y. Now that's good, but that's kind of a gimmick, and that doesn't really help you understand anything about logs, right? Maybe about traveling, right? If you want to be a travel agent or something, or if you have wanderlust. So that's not a bad thing to do, but I want to kind of explain it to you a little bit better, right? B, of course, is called the base of the exponential. That's pretty easy to spot, right? And we know that if the base is between 0 and 1 for exponential, it's exponential decay. If the base is greater than 1, it's exponential growth, right? And it's equal to y. So b is the base, and then x is the exponent, and it equals y. All right. So when you translate it, the pieces still match up. When you have a log, it's the same base. It's exactly the same base. So if you have, the common base 10 on the exponential, it's going to be log base 10. If you have e to the something on the exponential, it's going to be log base e, or the natural log. Okay. Now, here's what I want you to tell yourself right here. The log is nothing more than an exponent. That's all a log is. Okay. What is a log? It's an exponent. So for instance, if I ask you, what is log base 4 of 16? What is log base 4 of 16? You can see the answer there. Okay. The log is the exponent. Okay. So here's the log. The log is the exponent. Now, it's a special exponent. So the log is the exponent to which you must raise the base to achieve what we call the argument. Okay. So basically when you see, let's get rid of that 2. It's just too tempting to look at it. I know you know the answer already, but let's just get rid of it, right? Psychologically. When we say log base 4 of 16 equals something, here's how you want to read it. The log is the exponent. Okay. So we're saying 4 to what power is 16? That's how we read that. Okay. Another way. 4, the base, to what exponent or what power, right? Same thing. The log is the exponent. 4 to what power is 16, which we call that the argument, right? The thing that we take the log of is called the argument. That puts it into perspective then, right? So now when you see log base 4 of 16, it's not just like, I have no idea what that is. Hey, Landon, any tutors today, tuties? No, okay. Log base 4 of 16, you can say, 4 to what power is 16, right? 4 to what power is 16? Well, what do we usually do instead of a question mark in algebra? We put a what? We put an X. So 4 to what power is 16? Yeah, and now sometimes it's intuitive, right? 4 squared is 16. So guess what? The exponent is 16. I mean, the exponent is 2. 4 to the 2th power is 16. So the log is 2. The log is 2 because 2 is the exponent. All right. So that's all the log is. So when you're going back and forth, you could say, okay, if b is the base, x is the exponent, right? X is the exponent. So there it is. The log is the exponent. And the b is the base, okay? So then y is your argument. Let's try it out. You can still go back and forth, but the parts match up. The log is the exponent. Let's try it out. Evaluate the following quickly, right? Log base 2 of 8 without a calculator. Well, log base 2 of 8. That's how we read that. It's a number, right? It might be someone's jersey number. They don't even know it. What's the answer? 3. The answer is 3. Okay. And the answer is 3 because 3 is the exponent to which we must raise the base 2 to achieve our argument of 8. In other words, 2 to the third power is 8. Yep. Okay, so you can write it like that if you want, or this might be a good time to write it like this. Why? Because you could verify, right? You could verify by doing the around the world ditty that you like, right? Let's go on a short little trip. Field trip, everybody. 2 to the third equals 8. 8 equals 8. It sure does. Yep, sure does. Okay. Sure does. Now, that's one way to do it. That's one way to do it. Is there another way to do it? Well, absolutely. Let's come up here and review what we've already reviewed from pre-cal. The natural log of e to the x is x, which is the same as e to the natural log of x, right? That's very important. When you compose two inverse functions back to back, they undo each other, and we end up with what we started with. Well, if it works for base e, guess what? It's going to work for other bases. So in general, we could say this: log base b of b to the x is x, which is the same as b to the log base b of x. It works for any legal base. If the base is between 0 and 1, it's logarithmic decay, it's exponential decay. They both decrease. If base is bigger than 1, it's exponential growth, it's logarithmic growth. They both increase. Okay, so this just gives you another perspective. Look what we could do. If you wanted to figure out log base 2 of 8, and you didn't want to think about it in terms of what a log is, 2 to the what power is 8, if you can write the argument as a power of the base, it'll be the exponent. So you can write it like this: log base 2 of 8 is the same as 2 to the third, right? And now what is log base 2 of 2 to the blob? It's the blob. You get the same answer. Okay. So that's doing more of like the algebraic manipulation, whereas the left column is doing it more of the, I understand what a log is, right? 2 to what power? Either way, right? We'll do some more logs. This is why students tend to hate logs, because they're like, there's so many different things involved with them. Yeah, but that's what makes them also freaking awesome, freaking useful. All right, log base 3 of 1/81. Oh, what? -4. Kaboom. Yeah, kaboom. You're like that soap scum lime deposit purple bathroom spray right there. Just kaboom, right? Yeah. Or like the purple mopping liquid, Fabuloso. You're Fabuloso. Yeah. All right, now let's see why. Let's see why. You could look at this a couple of different ways. You could say that equals x. 3 to what power equals 1/81, right? 3 to what power equals 1/81. If you could turn a log equation by setting it equal to x, you made it into equation. If you could turn it into exponential, you can use the GT-BTS method. Does anyone know what that is? Did Ms. Skurhawk use that last year? It's because they're one-to-one. Yeah, it's an acronym. Get the bases the same. Get the bases the same method. Okay, Brody, look. It's kind of the same thing we did on the second column above. I have 3 to some power. Can I write the other side as a power of 3? Well, 81 is 3 to the 4th. And then I get 3 to the x if I bring it to the top, makes it 3 to the -4th. Well, look at there. Since these functions are one-to-one, if you have 3 to the x equals 3 to the -4th, you got the bases the same. You could say, so x equals -4 by the GT-BTS method. It's a consequence. Okay. That's one way to do it. Let me show you another way to do it. Let's say I have 3 to the x equals 3 to the -4th. If you don't want to use the theorem, which is get the bases the same, you can actually do it algebraically. I have x trapped in the exponent base 3. How do you unexponentiate base 3? Log both sides base 3. And remember, the log is an operation, so it has to go in the front. And now look at the left side. What do you think log base 3 of 3 to the x is? X. And on the right side, what's log base 3 of 3 to the -4th? -4. Yeah. So either way, The GTBTS is a theorem. The right side is algebraic. You can always undo, right? When you're solving an equation algebraically, it's always about peeling back the layers by doing the inverse operations in the reverse order, okay? Yeah, or you could go straight to it. Watch, you could go straight to log base 3 of 1 over 81. You could say, oh, that's log base 3 of 3 to the negative 4th, right? And that's using this theorem up above, the inverses, right? Log base 3 of 3 to the negative 4th then is negative 4. How did he just know it was negative 4? Well, that's what this is. Mason, here's kind of the sequence, right?
No, I know. I'm just questioning how you.
Oh.
I started doing it, I got it. Yeah.
Oh. I think every Pepper LEMC just knows that. Fist bump, boom. Oh, real one. Oh, real one. Oh, okay. Real one. I was going to do air bump. Yeah. Wow. That's good. That's good. All right. Go ahead and do this one on your own. On your mark, set, go. Log base 16 of 4. I don't care how you do it. If you want to set it equal to X and convert it to exponential. Very good. Very good. Very good. Set that equal to X up at the top. Be careful just with your notation. We've seen it a couple of different ways. If you see this right here, this is an expression, right? It's not an equation. So if you introduce a variable, you kind of have to turn it into an equation from the beginning, which is not a bad thing to do. That's equal to a number, but you could say, I don't know what that number is. That's what we do in algebra. If you don't know what something is, call it X. Now that you have an equation, now you can use that conversion formula, or you could say, the log is the exponent. So X is the exponent, right? You see that? The log is X. The log is the exponent. Therefore, by the transitive property, X is the exponent, right? So 16 to what exponent power is the argument for? It's like doing the around the world, but you're doing it with your understanding. Okay, now I got to make it smaller, right? 16 to the first is 16. That's too big. So it's got to be smaller than 1. What could it be? 1/2? Yeah. So at this point, you're like, oh, I know that 16 to the 1/2, right? How would you do it? You would write it as, would you just go X equals 1/2? You could do that without showing any work. That's fine. But here's what changing it to exponential does. If you're not sure that it's 16 to the 1/2, because that's the square root of 16, right? Which is 4. You could try to get the bases the same. Now, it's easier to make a number smaller than it is to make it bigger. So rather than try to build 4 up equivalently, let's see if we can get 16 down to 4 size. So I'm going to put this in parentheses, and I'm going to call 16 4 squared. Is that good? Isn't that another name for 16? Yeah, they're equivalent, right? And notice I have them in parentheses. Now, algebraically, when I raise a power to a power, what do I do with those? I multiply. So I get 4 to the 2x equals 4 to the first. Have I gotten the bases the same? Yes. Yeah. So now you either log both sides base 4, or by the theorem, you say, so 2x equals 1 by the GTBTS method. And now you solve for x and you get x equals 1/2. There's lots of ways to do it, okay? You just got to remember that the log is an exponent. If you set it equal to x, it's nice because converting it to exponential kind of makes it more of a routine algebraic problem. All right? Yeah.
So if you want to do the first line and then just jump straight to your answer,
Uh-huh.
you have to set your initial equation to x.
If you're going to introduce x anywhere, you have to introduce it at the top. Yeah. Otherwise, you're just doing this log base 16 of 4, and you're like, oh, 16 to the 1/2 power squared. Then you just write it like that. Or if you just know what it is, 16 to what power is 4? Oh, it's 1/2. Either one like that. So notice that this is an expression, and this is an expression, and here I have an expression, but I turned it into an equation when I wrote the numeric answer. Okay, these have no x's in them. If you're going to turn it into a conditional equation, and solve for x, you have to turn it into a conditional equation by saying it equal to x. That's a great question. Okay, that's what I was trying to point out with you. All right, so logs. This isn't even calculus, right? The calculus is still rumbling behind the door right there, right? Ready to run through before the game, and that bouncing inflatable unicorn, it's rumbling. Calculus is rumbling. We don't know its name yet. What would be a good name for that big rumbling unicorn that they run out of? Yeah, you already did say Harold. It looks like this.
That's exactly what it looks like.
Uh-huh. Yeah, and then yeah,
What a great name.
Harold, you said? I don't know.
Aren't you adjusting?
So we have Buford, we have Eugene, we have Eunice, and then the big bouncy guy. I don't know. I haven't gone up and asked him. He's kind of big and intimidating, but anyway, that's the calculus is rumbling. Like Westlake is waiting for their opponent, and we're rumbling behind here, bouncing around. Okay. All right. Example two. Example two. Ready? Sketch the graph of the following. Log base b, stating the domain and range. Okay, so this is just a real quick review. Just like with exponentials, if you have log base b of x and your base is greater than 1, it's logarithmic growth. Logarithmic growth. Okay, so if you're going to quickly sketch that for any type of parent function, you're going to want to kind of put your y-axis a little bit further to the left. Okay, so you're going to for sure have a vertical asymptote on the x-axis, and then it's going to come from negative infinity. It's going to look like that. And of course, this is the 0.10. Okay, so what would log base b of 1 be? What's the natural log of 1? 0. What's log base 10 of 1? 0. What's log base 7 of 1? 0. Let's see why. Log base 7 of 1. We're saying 7 to what power is 1? Is 0, right? 7 to what power is 1? 0. So every single one of them pass through the 0.10. Now, this is important to know because a lot of people think the domain and range are the same. They get them confused. The domain is going to be the set of all x such that x is strictly greater than 0. Strictly greater than 0. You can only take the log of a positive number. Okay? You can only take the log of a positive number. Why is that? Because, think about it. A number raised to any power can't be negative or 0. It has to be a positive number if it exists, right? But the range is what? All real numbers. All real numbers. Now, you can only take the log of a positive number, but can a log itself be negative? The log is an exponent, right? Can we have negative exponents? Yes. Okay. So keep that in mind. This is important. If you take the log of any number between 0 and 1, you're going to get a negative number. Okay. If you take the log of anything bigger than 1, you're going to get a positive number for logarithmic growth. All right. All right. Now, what if the base is between 0 and 1? Let's call this one g of x. This would be log base b of x, like log base 1/2 of x, or log base 0.2. It's going to be similar in the respect that it has, of course, a y-axis and an x-axis. It's still going to have a vertical asymptote on the y-axis, and guess what? It's still going to pass through the point 1, 0. But because the base is between 0 and 1, it's going to look like this. Yeah, that's going to be logarithmic decay. So the base of a log and the base of an exponential are the same in the sense that they determine whether it's increasing or decreasing, okay? And they have the same domain and range. The domain is still going to be everything strictly greater than 0, and the range is still going to be all real numbers. But if it's logarithmic decay, notice now if you take the log base 1/2 or the log base 2/3 of a number between 0 and 1, you end up with a positive number. Okay. So what's the difference between these two functions really? What's the difference between log base 7 of x and log base 1/7 of x? you can actually generate one from the other. They flip across the x-axis. Yeah. So reciprocal bases are x-axis reflections of each other. All right. Reciprocal bases are x-axis reflections of each other. All right. So again, here is just a summary of what we already said. If I inundate you with logs or inculcate you with logs, it's more likely to stick. The natural log of x is the same as log base e, and log of x is log base 10. Those are the only two that you can write without a base. And of course, x is what we call the argument. The thing that we take the log of is called an argument. But the log itself is a what? The log itself is an exponent. Okay. The log itself is an exponent, a special exponent, the exponent to which we must raise the base to achieve the argument. Right. All right. Here's a little factoid. Some logs become dugout canoes. Right. And then some dugout canoes don't get finished and become logs, firewood. Yeah. Did you know that? Dugout canoes. Very dangerous, dangerous. Teddy Roosevelt, yeah, they're dangerous. Teddy Roosevelt went all the way down the Amazon after he was president in several dugout canoes. It's a fantastic tale. If you ever want to read about his trek down the Amazon with his son Kermit, yeah, he had a son named Kermit. It's one of the most adventurous trails I've ever or journeys I've ever read about. Unfortunately for Gil Favor, Eric Fleming was his name. He was Gil Favor on the TV show Rawhide. I watched a lot of old westerns. Rawhide was the first show that Clint Eastwood was on. It was all about taking cattle, up the Chisholm Trail, from Texas up to Kansas and selling them. And the lead star of that program was Eric Fleming. He was a real, ruggedly handsome guy. And he was a bigger star than Clint Eastwood at the time, and he played Gil Favor, the trail boss. He was making a movie in South America, and there was a scene where he and a guy were in a dugout canoe going down the rapids, and it flipped over, and he lost his life, and they never released the movie. So very precarious. You don't want to do rapids in a dugout canoe. So, and it takes a while. You have to know what you're doing. You have to actually dig the wood out. So, some logs become dugout canoes and some dugout canoes become firewood. It's like, whatever, throw it in the burn pile. Yeah. Yeah. Look, maybe we can look at it. His name was Eric. I'll put a capital E, Eric Fleming. It's a tragic tale. Eric Fleming, also known as Gil Favor. He would have been more famous than Clint Eastwood had he not tipped over in a dugout canoe. He was actually in the military, and a giant weight, like an anchor, fell on his face and damaged it, broke all of his bones. And he actually had to have facial reconstruction surgery. And he actually became ruggedly handsome after the surgery. Like somehow they fixed him up and they gave him like this impressive jawline. But before the accident, he wasn't nearly as ruggedly handsome. So sometimes plastic surgery helps,
There are 23 million usable results.
When you Google Eric Fleming, there's 23 million. Wow. Wow. Like I said, I mean, he would have been a bigger star today than Clint Eastwood if it weren't for a dugout canoe. But anyway, Teddy Roosevelt, he and his entire crew went all the way down the Amazon. Good reading. All right. Let's keep going. Example 3. Use the properties of limits to find the limit of each of the following. Okay, so now we're kind of dipping into a little bit. Did you find something naughty?
No.
Oh.
It looked like Mr. West, kind of.
Oh, I don't know who that is.
He's a government teacher here.
Oh, Mr. West. Yeah, he was teacher of the month for the dancers.
Yes.
Yeah, that West. Yeah. Okay. He does kind of look like West. All right. The limit as x goes to infinity of. This is composition, right? It's not the natural log of x. So does College Board, is it okay in College Board if you actually plug in infinity? Does College Board like that? No, they freak out. But is it okay to do it off to the side on our workbench? Yes. Okay. So let's think about it. What would infinity squared minus infinity be? Yeah. Well, remember, if you have multiple terms and you're going to infinity, all you need to do is really look at the leading term, right? Like for polynomials, whether it's a ratio of them or not. So x squared is going to dominate. So what's infinity squared? infinity. Now, what's the natural log of infinity? Not probably. Remember, the natural log of infinity is the same as what's the limit as x goes to infinity of the natural log. It's the same thing. What do all log functions that are growing go to? Slowly. They go to infinity, very slowly. Okay. So that would be the answer. Okay. So you can put infinity, or I heard you say it, Ansley, DNE, right? All right. So don't plug in infinity directly below the answer, because that's it's like using ain't in a formal paper. You can kind of maybe do it in your rough draft or whatever, but you have to use different words. Okay. All right. So that's fine. This is composition. That, notice how much faster and easier that is than this. This is really what would be the alternative, the natural log of the limit as x goes to infinity of x squared minus x, right? That would be composition. And then if you evaluate the inside, that's a parabola that opens up. So that goes to infinity. So that output of infinity becomes the new input of infinity as we approach the next layer. And notice, if you were doing this on a free response, that would be the notation you would have to show if you showed anything below it other than the answer. Okay. But if you go off to the side on das Birkenbenchen, then go ahead and plug in your infinity. All right. All right. Letter B, the limit as x goes to 9 of, from the right-hand side, look at that, of log base 2 of x minus 9. Oh, crap. Well, let's try direct substitution, right? Never not first. 9 minus 9, 0. What's log base 2 of 0? Well, the function is undefined there, but what's the limit? Is it negative infinity or positive? You're positive it's negative? Oh man, crap. Maybe. I think so. Let's try it. Let's look at it this way. The parent function is log base 2. Is that growth or decay? It's growth. What does the minus 9 do to any function, including logs? Shifts it. No, it's inside. It's right. Yeah. If this were closed and that parenthesis weren't there, then it would be down. Okay. All right. So that's, if you come up to the side and do your graph, the vertical asymptote used to be at 0. It's now shifted to the right 9 units. So it's right here at x equals 9. And log base 2 is growth. So there's what the graph looks like. Now, Hank, yes, as we approach 9 from the right, we're going down, down to down, down, negative infinity, or DNE. These are really good multiple choice questions, by the way, because we don't want people to just upgrade from IDK to DNE, right? Like fancy poo. Yeah. We actually want to test them and maybe give them a 50-50 shot if they're not sure. All right. Now, is that the only way to do that? Probably not. Let's see the longer way. If it's composition and you take it in, you could do log base 2 of the limit as x goes to 9 from the right of x minus 9. All right. Now, let's think of that. X minus 9, you have to know what the graph looks like, right? Here's negative 9. The slope is 1. We're approaching 9, which is right here from the right-hand side. So as we approach 9 from the right-hand side, we're approaching 0 from what side? Above or below? Above. And remember, that translates into, when it becomes the input, the limit as x approaches 0. This is where we had that really important discussion where a one-sided limit can change to a different side. But in this side, it doesn't, right? Because when you're approaching from above, that's considered the positive side. So the output of approaching 0 from the positive side now becomes the input for approaching 0 from the positive side for the next layer of log base 2 of x. Right? And now if you think what log base 2 of x looks like, without the shift, it looks like this. And as we approach 0 from the right-hand side, we're approaching what? We're going down to negative infinity. Right? So that's the other way to do it, composition. But you don't have to go to that extent. You don't have to go to that extent. Right? All right. So this is kind of like calculus. The limit as x goes to pi halves from the left-hand side of log of tangent of x. Right? I know you're thinking, oh, it's DNE, right? But on the test, what if you have negative infinity infinity instead of D and E? What are you going to do? Or non-existent, they might have. And if there's numbers, what are you going to do? You're going to be like, skip it. No. Let's actually do this one by composition, right? Let's go ahead and write it. Let's bring this on the inside. So we have log of the limit as x goes to pi halves from the left of tangent of x. And by the way, what's the base here? On the log? 10. Yeah, I'm going to go ahead and write the 10. It helps. Bless you. But this is kind of when you have composition and you do it like this is kind of the divide and conquer. Now I can just think of tangent of x. Is that a graph that you're responsible for memorizing or knowing? It sure is, right? It's your monotonic increasing one. It looks like this, and it has a vertical asymptote at pi halves, and then it's monotonic increasing like that. And then there's 3 pi halves, and there's another one over here at negative pi halves. So every odd pi halves, 1, 3, 5, 7, 9 pi halves, there's vertical asymptotes. And in between there at pi, 2 pi, there's zeros. So what is the limit as we approach pi halves from the left? It's going to infinity, right? It's going to infinity. So that would be the same thing as saying what would be the limit as x goes to infinity of log base 10 of x. But what does that answer? In other words, what's log of infinity? It's going to infinity, right? Or DNE. Yeah. Divide and conquer, right? Last one before lunch, A, B, C, D, 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 D. You do this one on your own. I'll do it as well.
Hey, Ryan. Stop. Man, come on.
All right, there's one more minute left. So composition, bring it inside. I tried to make my G like this Times New Roman G, right? Bring the limit inside. So you got log base 10 of the limit as x goes to 0 from the right of cosine. Now, you can use direct substitution here, right? Cosine of 0 is 1. It's not a big deal. But because it's a one-sided limit, you'd want to be careful if you're approaching 1 on that particular side from above or below. So just FYI, cosine is chala, right? So there's chala. It starts high. As you approach 0 from the right-hand side, you're actually approaching 1 from where? Above or below? You're actually approaching 1 from below. So that output of 1 from below turns into approaching 1 from the left. It changes. Yeah. Now, is it really of any real consequence here? Not really, because log base 10, has a vertical asymptote and it goes like this. So as you approach 1 from either side, left side or right side, you're still approaching the same value of what? 0. Yeah. But we do want to be mindful of this, of the switch. Okay. Composition, one-sided limits. All right. Perfect timing. All right. We're getting ready to bust out the calculus on example 6. Okay. Have a good lunch.